Hello everyone, and welcome to a quick review of impulse and change in momentum. You might remember last year I set up a little demo for you in which I had a cart and a motion detector and a force probe. So there's the force probe over there and the motion detector over there. And basically I pushed the cart into the force probe. And the motion detector measured the velocity and the force probe measured the force. And so what we compared was the change in momentum of the cart. Remember, change in momentum is of course final minus initial momentum. And momentum is mass times velocity. So this is mass times final velocity minus mass times initial velocity. We can factor out an m. Final velocity minus initial velocity is change in velocity. So a couple different ways here of writing change in momentum. Final minus initial momentum and mass times change in velocity could also come in handy. And we compared that change in momentum to the area under the curve of a graph of force versus time, which we got with the force probe. Now I'm not going to redo that for you because you saw it last year, and hopefully you remember that those two things were equal to one another. And this didn't really seem to matter what kind of a collision we actually made. You know, I used springs, I used clay, I used magnet ends, and in every case, the area under the curve of the force versus time graph and the change in momentum was always equal. So we ended up with a force versus time graph that had a spike on it. So of course the area under the curve was that area which we could get the computer to do. But of course that's kind of hard to deal with because it's not a constant velocity. So last year, a constant force. So last year we talked about, well, what would it look like if it was a constant force? If, in other words, the force, right, was a horizontal line throughout that entire time period. Well, we decided that that would be the same area, and that would be what we would call the average velocity. So the average velocity is the constant force that has the same effect as the spike. This, of course, would be the change in the time, and so the area of this rectangle would be average force times time, or constant force times time, if you will. And so that is what we defined as impulse. Impulse is defined with a capital J. I don't know why, but it is. And this is the area under the curve of a graph of force versus time, or it's the constant force times the change in the time, or, if you're looking at this, we'll get to the calculus momentarily. Units of impulse come right from the equation. It's force times time, so newtons times seconds. And this is equal to the change in momentum. So the constant or average force times the time is equal to the change in momentum. This is what is known as the impulse change in momentum theorem. It's a great name, isn't it? And they're basically equal to one another. And this again is for a constant or average force. Units, Newton seconds. For the impulse, change in momentum is mass times change in velocity, so that's a kilogram meter per second. Now you might say, but wait a minute, how could those be equal when the units aren't the same? The answer is, they are the same. Remember that a newton is a kilogram meter per second squared. The force required to make a 1 kilogram object accelerate at 1 meter per second squared. So canceling out the seconds, we get a kilogram meter per second. So they're really equivalent units. But be careful. If it's an impulse, the proper units are Newton seconds because an impulse is a force through a time. If it's a momentum, it's a kilogram meter per second because momentum is mass times velocity. Sometimes the AP tests will get a little sloppy with those. I never will. Right? I like to keep my units what we're talking about. So, those two things being equal to one another, we can write this in calculus as well. If the impulse is the area under the curve of a graph of force versus time, that's the integral of the force with respect to time. On the computer, we could find that area analytically, but of course, if we've got a force function as a function of time, right, we can then calculate the impulse, and that would be equal to the change in momentum. So this is the calculus version of the impulse change in momentum theorem. Impulse, again, is the area under the curve, so the integral of force with respect to time. So you can define impulse as F delta t if it's a constant or average force, and as the integral of force with respect to time if it's a non-constant force. Units are still Newton seconds, of course. Impulse change in momentum theorem, calculus version. So we now have two ways of calculating impulse and relating it to the change in momentum. And you have to be real careful again as to whether the force is constant, first version, or non-constant. Then you need the calculus. And from all the demos we did, of course, it held in any type of collision. And last year we talked about two different kinds. We had elastic collisions. Elastic collisions are ones in which kinetic energy is conserved. In other words, there's no dissipated energy during the collision. This would have been represented by magnet ends. So the cart and the probe never actually touched, okay, but the magnets conserved the kinetic energy. Most collisions are not elastic. Never assume that a collision is elastic unless it tells you or it gives you some evidence. Most collisions dissipate some energy, and they are what are known as inelastic collisions. This would be the normal collision with the cart and the spring, say, or an extreme case would have been the cart with the clay, where it actually came completely to a stop and all of the energy was dissipated. And remember that that dissipated energy usually gets stored as thermal energy or sound. Now, two versions of the proof of the impulse change in momentum equation. First off, the non-calculus version. For constant or average forces, Newton's second law says the net force acting on the cart has to equal ma. But of course, remember that acceleration is change in velocity over change in time. Right? So we can plug that in. So we get net force is mass times the change in the velocity over the change in the time. Well, if this is what is known as a closed system, and a closed system means no change in mass. So remember, isolated means no external forces. Closed means we keep track of all the mass. None of it flies away somewhere where we don't keep track of it. Then we can plug the mass into the change in velocity part, and we get the change in the mass times the velocity over the change in the time, because the mass is just a constant here. And of course, mv is momentum. This is actually Newton's second law. Newton didn't write force equals mass times acceleration in his Principia. He wrote force is the rate of change of momentum, which is what we found here. Right? Force equals the change in the momentum over the change in the time, the rate of change of momentum. And if we multiply by the change in the time, we get the impulse change in momentum equation for constant forces. Similar proof, but for calculus, since this is AP. Net force equals mass times acceleration. Acceleration can, of course, be written as the derivative of the velocity with respect to time for non-constant velocities. If the system is closed, we can factor in the mass, and we get the derivative of mass times velocity with respect to time. But mass times velocity is, of course, momentum. So we get the calculus version of Newton's second law, which says force is the rate of change of momentum, or the derivative of the momentum with respect to time. Right, so this is for non-constant forces and non-constant momentums. Now, we have to do a little fancy calc here to get to the impulse change in momentum equation. First of all, take the integral of both sides with respect to time. Right, you can do that. There's an equal sign, so you can do the same thing to both sides. Notice that the delta t's cancel out. So we're left with the integral of the force with respect to time is equal to the integral of the momentum, and we do that from the initial momentum to the final momentum. Well, the integral of the momentum is just momentum. That's a 1, right? So if you use the power rule, you're adding 1 and dividing by 1, and you get momentum, evaluated from the upper limit minus evaluating it at the lower limit. But final momentum minus initial momentum is just change in momentum. So this is just the impulse change in momentum equation for calculus. Check out the calc here and look at what we did, right? And you can see that we can use it then either way. But again, we have to be careful. Are the forces constant or average, or are the forces non-constant? Then we have to use calculus. Hope you enjoyed this quick little review of impulse and change in momentum.